Design and Analysis of Algorithm. Unit 6. Multi-threaded and Distributed Algorithms. Introduction to multi-threaded algorithms. Parallel computing is achieved through static threading, which provides software abstraction to the processor. Threads can be considered as a lightweight process, sharing a common memory assigned to the program in execution. The execution of each thread is independent of each other and they have their program counter. Threads are scheduled similar to the process. They may be swapped in and out as and when required. Dynamic multi-threading. It allows the programmer to specify parallelism in the application without worrying about communication protocols, load balancing, etc. The scheduler takes care of load balancing, which will reduce the burden on the programmer. All dynamic threading supports two features: nested parallelism and parallel loop. Nested parallelism allows a subroutine to spawn and allows the caller to proceed parallel. Parallel loops are simple loops that are executed parallelly. Parallel algorithms are an extension of serial algorithms. We can extend the serial model to parallel by including concurrency keywords parallel spawn and sync. Performance measures. The theoretical efficiency of the multi-threading algorithm is measured using two metrics: work and span. Work. It is the total time taken by the entire computation to execute on a single processor. It is a summation of the time taken by each strand. Span. It is the longest time to execute a strand along any path in computation. Execution of a multi-threaded algorithm does not depend only on work and span, but it also depends on other parameters like the number of processors and how the scheduler assigns strands to the processor. Let T denote the running time of an algorithm on a P processor. Work represents the execution time on a single processor, so work on it, I, A2 processor takes T of I, time. Analyzing multi-threaded algorithms. 2 points should be considered while analyzing multi-threaded algorithms. A. Analysis of work. B. Analysis of spawn. Analysis of work is nothing more than the analysis of simple serial algorithms we discussed so far, so analysis of work is not much challenging. It is a running time analysis of serialization of the multi-threaded algorithm. Parallel loops. Many real-life problems involve loops. Loop is the primary component contributing to the complexity of the algorithm. Loops can be parallelized using spawn and sync keywords. However, it is customary to use parallel keywords in front of for keywords. Race conditions. Algorithms are said to be deterministic if it always does the same work for the same input, irrespective of how the instructions are scheduled on a multi-core machine. And they are said to be non-deterministic if the behavior might vary on each run. The deterministic multi-threaded algorithm often suffers from determinacy race. A determinacy race occurs when two logical parallel instructions access the same memory location and at least one of them performs a write operation. Multi-threaded merge sort. Merge sort is a popular sorting technique which divides an array or list into two halves and then start merging them when sufficient depth is reached. Time complexity of merge sort is O of n, log n. Threads are lightweight processes and threads shares with other threads their code section, data section and OS resources like open files and signals. But, like process, a thread has its own program counter, PC, a register set, and a stack space. Multi-threading is way to improve parallelism by running the threads simultaneously in different cores of your processor. In this program, we'll use 4 threads, but you may change it according to the number of cores your processor has. Distributed, breadth-first search. A distributed algorithm is an algorithm, run on a distributed system, that does not assume the previous existence of a central coordinator. A distributed system is a collection of processors that do not share memory or a clock. Each processor has its own memory, and the processors communicate via communication networks. We will consider two problems requiring distributed algorithms: the coordinator election problem and the value agreement problem, Byzantine generals problem. Distributed, breadth-first search. The graph is very useful to represent the relationship between data objects. Graph search plays an important role in analyzing a large data set. Breadth-first search is often used to find the shortest path between a pair of vertices. Level synchronized algorithms proceed level by level, starting with the initial vertex. The level of any vertex U is the distance of U from its source vertex V. Distributed, minimum spanning tree. Given the connected graph G, V, B, the spanning tree is the subgraph of G such that it covers all the vertices of G and it does not contain the cycle. Given the weighted connected graph G equals V, U, the minimum spanning tree, MST, of graph G is the spanning tree that has minimum edge cost. W represents the weight corresponding to edges in E. Many sequential algorithms have been proposed to find MST. Prince and Kruskal are the most popular among the set of such algorithms. Distributed minimum spanning tree problem involves the construction of a minimum spanning tree over a network utilizing distributed algorithms. Nodes in the network communicate with each other by message passing. String matching. Introduction. String matching algorithm is also called string searching algorithm. This is a vital class of string algorithm is declared as this is the method to find a place where one is several strings are found within the larger string. The Rabin-Karp algorithm. The Rabin-Karp string matching algorithm calculates a hash value for the pattern, as well as for each m-character subsequences of text to be compared. If the hash values are equal, the algorithm will analyze the pattern and the m-character sequence. In this way, there is only one comparison per text subsequence, and character matching is only required when the hash values match.